This short video is a step-by-step solution for the example entitled Applying the Mass-Rate Balance to a Feed Water Heater at Steady State. Let's first look at the problem statement as given to us. A feed water heater operating at steady state has two inlets and one exit. At inlet 1, water vapor enters at P1 equals 7 bar and T1 equals 200 degrees C with a mass flow rate of 40 kilograms per second. At inlet 2, liquid water at P2 equals 7 bar, T2 equals 40 degrees C enters through an area A2 equals 25 square centimeters. Saturated liquid at 7 bar exit at 3 with a volumetric flow rate of 0.06 cubic meters per second. We're asked to determine the following: the mass flow rates at inlet 2 and at the exit, both in kilograms per second, the velocity at inlet 2 in meters per second. Let's do a critical read of the problem statement as given to us, highlighting in red the important information provided to us and in green the information requested. A feed water heater operating at steady state has two inlets and one exit. At inlet 1, the conditions are given in terms of water vapor, P1 equals 7 bar and T1 equals 200 degrees C, and a given mass flow rate. And inlet 2, we know it's liquid water at the same pressure, temperature T2 equals 40 degrees C, entering through an area A2 equals 25 square centimeters. Saturated liquid at 7 bar, exit at 3 with a non-volumetric flow rate. We asked to determine the following: the mass flow rates at inlet 2 and at the exit, both in kilograms per second, and the velocity at inlet 2 in meters per second. Let's start to develop the solution. The first thing we need to do is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement in a more compact bulleted list form. A stream of water vapor mixes with a liquid water stream to produce saturated liquid stream at the exit. The state at the inlets and the exit are specified. The mass flow rate and volumetric flow rate data are given at one inlet and at the exit, respectively. The next thing we need to do is to summarize what we have to find. This is essentially the same information we highlighted in green in our critical read of the problem statement, presented again in a compact bullet list form. The mass flow rate at inlet 2 and exit in kilograms per second, and the velocity V2 in meters per second. The next thing in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few key pieces of information which will guide us towards our solution. The first thing to recognize is we have mass flow rate entering and leaving the feed water heater. This immediately suggests that a control volume approach is relevant. Having recognized this, we need to select a control volume boundary. Remember that control volume is defined by a virtual boundary that can be picked as desired to tie in the information provided to the information requested. In this case, enclosing the feed water heater and cutting through the mass flow rates in and out of the feed water heater is a very sensible choice, as delineated on the schematic with a red dashed line. The choice of the control volume clearly ties in all the information provided. The next step is to develop an engineering model. In other words, a set of assumptions needed to perform the analysis of the problem. The control volume shown in the previous diagram is at steady state, and one-dimensional flow is assumed at the inlets and the outlet. Having completed all the preliminary steps required of all problem solution, let's develop the analysis. The principal relations to be employed are the mass flow rate balance and the expression for the mass flow rate. At steady state, using assumption 1, the unsteady term drops out and the mass rate balance becomes that the algebraic sum of the inflows and outflows is equal to 0. Solving for M2 dot gives us the following expression. Now, the mass flow rate M1 dot is given. The mass flow rate at the exit can be evaluated from the given volumetric flow rate using assumption 2, where V3 is the specific volume at the exit. Using the table of the properties of saturated water, you can look up the specific value of the specific volume at the exit, and substituting, we get the mass flow rate M3 dot at the exit is equal to 54.15 kilograms per second. The mass flow rate at inlet 2, M2 dot, is then given by the following expression, where M2 dot is equal to 14.15 kilograms per second, which is the first answer we are seeking. For one-dimensional flow at inlet 2, the expression for the mass flow rate as a function of the volumetric flow rate can be substituted. Hence, we can get the value of the velocity V2 by the following expression. State 2 is a compressed liquid. The specific volume at this state can be approximated by the specific volume for saturated liquid at that temperature. From the pressure table of properties of saturated water, we can find the value of V2 at 40 degrees C. Evaluating the numerical expressions for V2 and paying attention to unit conversion, we get the following. V2 is equal to 5.7 meters per second, which is the second answer we are seeking. In closing, I would like to make a few comments. In accord to the mass balance equation, the mass flow rate at the exit equals the sum of the mass flow rates at the inlets, as shown in the expression below. However, the volumetric flow rate at the exit does not equal the sum of the volumetric flow rate at the inlets due to the very different values of the specific volume. Stream 1 is a vapor, and stream 2 and 3 are liquid. This last point is left as an exercise. By numerically evaluating the volumetric flow rates, this can be verified as shown below. This concludes the step-by-step solution of the example entitled Applying the Mass Rate Balance to a Feed Water Heater at Steady State.